And next up is Yifei Luo.
Oh, thank you. All right. Thank you for having me here. So I'm Yifei Luo. I'm a grad student here at Santa Cruz. I'm very glad to introduce this new Merian Survey to all of you. I think this is actually the first time we actually introduced Merian Survey at a conference, so pretty nice that I can do that at Santa Cruz. So the Merian Survey is a new medium and survey. It's to honor a 17th century, say, naturalist, Merian. Actually, she's one of the very first female scientists, and also she studied tiny insects, butterflies, and worms. So actually, we saw like dwarf galaxy also is kind of tiny little galaxies in the universe. So we use this butterfly to be our logo. So the co-PIs of the Merian Survey is my advisor Alexi Liatold and Jenny Green at Princeton. We have a pretty nice group collaborators working on this survey. So I will first very briefly give you an overview of the survey, and we'll talk a little bit about background and the current status of the survey. So the core science goal of the Merian Survey is to build a very large sample, 100,000 dwarf galaxies at about redshift 0.1. When I say dwarf galaxies, actually in the bright dwarf regime, so 10 to the 8, 10 to the 9 solar masses. So we got 62 full nights on the dark energy camera. It's on the 4 meter telescope in Chile. We built 2 Cosmic-made medium band filters, N708 and N540, to target H-alpha and O3 emission lines for those galaxies at this redshift range. And we will cover, we hope to cover about 800 square degree in the HSC SSP wide field. So all of our galaxies will also have pretty deep HSC broadband data. Okay. So I don't think I need to convince any of you that dwarf galaxies are interesting, and especially like people have been giving several talks about the interesting, say, discrepancy for, especially in the bright dwarf regime, that you see quarks versus core, cusp versus core, and other, say, discrepancy in rotation curves and something like that. So this is basically the mass range, roughly, that the Merian Survey would probe. So, and also, so we know there's discrepancies in the halo profile, and also it's pretty, I would say, less constrained in the stellar mass halo mass relation in the low mass region. So the point is, we wanted to say constrain the halo properties of those dwarf galaxies. So previously, as many of you actually have been working on, is to use rotation curves to constrain the halo properties of dwarf galaxies. But the thing is, we know the dark matter halo is actually quite large, and the baryon only basically rotate at the center of the halo. So what we are measuring is really actually the center of the halo. So any, say, halo mass is actually extrapolated from the center, say, kinematics. And also for those dwarf galaxies, their kinematics can be pretty chaos. It might even have very little rotation, so it's make life much complicated to do this. So to do that, well, stopped. Okay, here. So alternatively, there's another very powerful way to constrain halo properties, to use the weak gravitational lensing or galaxy-galaxy lensing, which large surveys. But so to do this, we need a large sample to stack, basically, to get a decent signal. So previous surveys like Sloan or even DESI are not really, say, deep enough to get a large sample of dwarf galaxies with a pretty complete sample. So but actually, in the next generation, this generation is ongoing, large and deep surveys such as HSC, we actually will be able to form a pretty large and complete sample of dwarf galaxies down to 10 to the 8 at a reasonable cosmological redshift range. For example, this plot is showing you the mass completeness as the dividing line here for several surveys, such as HSC, Rubin, and Roman, and above that it's pretty complete. So we're just showing you here is actually our Merian redshift and mass range. So with HSC, large and deep imaging data, we will be able to detect those dwarf galaxies with a pretty high completeness. So in a paper Alexei led 2 years ago, so we actually use a pretty standard way to estimate the lensing signal noise or lensing covariance given, say, the number of dwarf galaxies that we could probe in different surveys. And here is a predicted lensing signal to noise, well, lensing profile. We basically use the Mach profile from Borfry simulation and add the lensing signal noise bar at different radius beams for different surveys. For example, HSC would be the first kind of survey would be able to detect have a reasonable lensing signal noise about 30 or 40 within, say, 500 kiloparsec of the dwarf halos. So this is actually, for the first time, we will be able to have a large enough sample, and very importantly, complete sample out to, say, redshift 0.1 to measure the weak gravitational lensing signal around those dwarf galaxies. However, as I just put those 4 surveys, HSC, Euclid, Roman, and Rubin, they're all imaging surveys, broadband imaging surveys. So basically, we only have broadband photoses for most of them. Some of them might have spectra, but most of them would only have photoses. So, but the thing is, it's really, so the broadband photoses at, say, redshift 0.1, 0.2, they are not good enough to measure lensing. So for Merian, a very important problem is how to get a decent, say, redshift for those galaxies. We know those dwarfs are there. Their signal noise might be all right, but how do we find them? How do we have a decent precision for the photoses? So the idea is for those, say, bright dwarfs between 10 to the 8, 10 to the 9 solar masses, the quenching fraction is actually pretty low. From different, say, field dwarfs or satellite dwarfs, most of them are actually star forming, so they would have a decent, say, emission lines, for example, H alpha and O3. So then the idea is, okay, we probably could build a medium band or narrow band filters target specifically at, say, H alpha and O3 emission lines to help improve the photoses to do lensing. So here's the idea. So there will be a trade-off, say, in the filter designs. So if you go narrower and narrower for the medium band or narrow band filters, your signal from the emission lines will be higher and higher. You can better and better constrain the photoses with the help of the narrow band filter. But the thing is, the narrowband filter, the filter width also corresponds to the range of the redshift space. So you got smaller and smaller volume. So you got less dwarf galaxies that you can stack to measure the weak gravitational lensing. But if you go wider, the emission line signal can also, say, smeared out from the continuum. So we have to find basically a balance, a compromise between the say, filter width and also the central wavelengths, because if you go higher and higher, the dwarf galaxy would be fainter and fainter, so it's also hard to detect. So to say, simulate, to optimize the filter design, we built a simulation. So basically to simulate the fluxes of dwarf galaxies given filter design, basically given the filter central wavelengths and filter width. So we generate our own SEDs, dwarf SED libraries with the Cosmos 30-band photometry, because it's rather complete and have pretty nice, say, a lot of photometry to constrain the SEDs with Prospector. So this is our mock SEDs, and they have, say, kind of realistic H-alpha equivalent width, and also other emission lines. And we use a software called Gaussian to simulate the images given, say, telescope, say, response curve from CCDs, from primary, from sky emission lines, the lot. So we can simulate pretty, say, kind of realistic dwarf galaxies and simulate their fluxes. So now we ask, say, at different, say, filter designs, say, filter center versus filter wavelengths, filter width, what's the wave cleansing signal to noise we can get from varies from different, say, filter center and filter width. So it turns out there's so the optimization prefers, say, the filter center, and this is for H-alpha, between redshift 0.04 and 0.1. So this is expected. If you go higher and higher in redshift, the dwarfs are fainter and fainter, and it's hard to detect. And if you go lower, the volume is smaller, so you don't have, say, many dwarfs to stack. And also, there's a peak at a pretty large filter width, about, say, 800 angstrom. So this is actually not very realistic, because so this is basically actually like a broadband filter. So, but the thing is, this is only the simulation. Simulation would have enough, say, signal noise if you have a very long exposure time, but realistic photometry wouldn't have a very, say, so the photometry would always have some systematics, like systematic error, for, say, for like 0.1 magnitude or so. So we basically choose the lower or smaller filter width pick here at redshift 0.08 and about 300 angstrom. So this is basically how we choose our filter set. And this is the H-alpha filter in 708 and the corresponding O3 filter are the same redshift range, but for O3. And their comparison to the HIC, the other 5 broadband filters. So the two filters were made by Asahi Filter Company and directly shipped to Chile. So for those, with the help of those two, say, medium band filters, if we rerun the SED fitting, we're actually PhotoZ with this 7-band, that's a GRIZY plus N708 and N540, we actually got a pretty nice PhotoZs with a PhotoZ scatter about 0.01. So this is from our mock photometry without any systematic, say, uncertainty. So this is basically the best we can achieve, but we don't know really we can achieve that or not. But this is definitely way better than the HIC 5 broadband PhotoZs, because they got like a scatter about, say, the sigma of PhotoZ about 0.5. So our Merian survey would cover, as I mentioned, cover the HSC wide field with basically 60 full nights. So it's already started during the pandemic. We're still actively, say, collecting the data. And we're about halfway through the survey, so it's just about achieved like 50% of our say, pointings. And we're also developing our data reduction pipeline. So this is led by our Princeton collaborators, Robert Lupton and Calvin Lee. So we basically we are using LSSD pipeline to reduce our raw data and also tie the photometry of Merian narrowband to the HSC broadband filters. So this is just very preliminary results. So so before we run PhotoZs, let's look at some, say, flux axis. for example, like a I-band minus N708 color. So this on the bottom is the mock photometry from our simulation, and this is actually real data. So you can see we actually are selecting those dwarf galaxies at redshift 0.1. But you also will see we have some contamination at higher redshift, but this can be ruled out basically using our O3 filter N540. Okay, so and this is also a very preliminary photo Z position. So with a SPECZ sample, well, we build in Cosmos area. So we have redshift SPECZs from different surveys, and we're also collecting our own SPECZs. So we use this SPECZs versus photo Zs, and the scatter is actually 0.05. So it's not 0.1, so not achieved our goal, but it's still, I mean, pretty good for weak lensing measurement. And we are still working on it, trying to see if we can improve it. Okay, so I think I still got some time to talk a little bit about the, 1 minute, sure, yeah. So it's just our science goal. So I think I've mentioned to measure the weak lensing signal around dwarf galaxies. We can also constrain the mass size relation for those dwarf galaxies because we have deep HSC images. And we are also collecting spectra. We already got about 2,000 spectra from UC-HiPACC and Magellan through different programs, and we are trying to measure the emission line properties versus the fluxes that we could see in the Merian narrowband filters, well, medium-band filters. So this is a preliminary result by a grad student, well, just finished her PhD at Princeton, Erin Kettle-Fong. So basically, she just subtract the continuum from the medium-band filters, so we can actually see some residual emission lines, and we can compare the emission lines versus the emission line we actually measured from the spectra, and it actually show a pretty nice relation. So we believe we can actually constrain the emission line properties from the medium-band images from our Merian survey. And the last thing is we can actually measure, well, actually find some higher redshift Lyman alpha emitters with our N708 and N540. So this is a preliminary work led by a collaborator at Tsinghua University. So they find 2 Lyman alpha emitter at redshift 4.8 and 3.4. And here is, we are showing basically the green is our say N708, and this is N540 emission line. So they are pretty bright in our medium-band filter. So we believe we can do some other interesting science cases with Merian data. Okay, I will leave you the summary and take questions.
Thank you, Yifei. We have time for maybe one question while our next speaker sets up. Maybe we'll have 2 questions.
Thank you for the nice talk. So if you can fine-tune your filters so well, why not use multiple narrow filters that are like close by so that you have a wide range in redshift but also a nice resolution?
Yes, actually some, there are actually some programs doing this, but the thing is you have to build the filters, right? So it takes money, so and also the observation time. But yes, this is actually a very good point, and I think we should actually pursue this in future, say large imaging surveys like say LSST or Roman or something like that. You know, narrowband filter could be very powerful. Yeah.
Quick question. The forecasting for the weak lensing, are you assuming that all your dwarfs are centrals? And are you trying to avoid satellites by, for example, avoiding dwarfs that are nearby brighter galaxies? Or have you thought about that?
Yes. So basically, right. So we have to model this, basically do some forward modeling from, say, Bolshoi or some other simulations to see. So these, like in lensing, there will be 1 halo term, 2 halo terms, something like that. But so this is also relevant to our photo Z position. So if our photo Z position is high enough, we actually can constrain the environment of those dwarfs. And also we have, say, Sloan or DESI, on the sky, so can also, with SPECZ, but for like more massive galaxies, can also help to determine the environment of our dwarfs. Yeah, we have thought about this.
Okay, let's thank Yifei again. And our final speaker before the break will be Alexandra Mannings.
Okay. Thanks. Hi, I'm Alexandra